like to welcome you to our first nuclear colloquium of the semester. And today we're very lucky to have Wei Li coming up from RHIC to give us talk. It's a very pretty campus if you ever get the chance to see RHIC. Wei got his PhD at MIT in 2009 and then started at RHIC in 2012. And I'm very lucky to be very privileged to work with Wei on the CMS experiment. And I very much like his introductory slide because I think about 50 years ago, T.D. Lee showed a picture of a nucleus and a Bunsen burner and said if you maybe could heat up a nucleus, who knows what would happen. And people laughed at him and said this could never, experiments could never do such a thing as heating up the nucleus. And so he's done it. So this is Wei Li from RHIC.
Okay, so can you hear me okay in the back? Yes. Okay, so thank Michael for the introduction. Maybe too much. I don't know. Okay. So this is my first time in Lawrence, although I have been collaborating with the Kansas nuclear physics group for many years, since the start of the LHC program, especially with Steve's group. Actually, I don't even remember how many papers we have worked on together. So it's really a great pleasure to visit here. So today I'm going to tell you about a soup that we have been cooking at the LHC, and we call that the primordial Quark-Gluon soup. So speaking of a soup, and you can think what first comes to your mind. So first of all, so soup is usually hot. So indeed, the soup we are making at the hadron collider is only several trillions degrees in temperature. And then the soup is a fluid. It can float. So these are the essential features of the Quark-Gluon soup that we are trying to study. So I'm going to explain to you so why this is so interesting and exciting, and what is mysterious about this soup, and in particular, I'm going to present you some recent results we have obtained at LHC, which may provide us new insights to try to understand the mystery. So I'm going to start with some basics, and so we know that in the subatomic world, the quarks and gluons are the most fundamental building blocks that make up a hadron. The three quarks make up a baron, and two quarks make up a meson. For example, the protons and neutrons, they are barons, and they build up a nucleus. So the size of a hadron is on the order of 1 Fermi, or 10 to the minus 15 meter, whereas the size of a nucleus is about order of magnitude larger. So these are numbers that are good to keep in mind, which you will see again later on. So the quarks are bound together by a force called strong force by exchanging the gluons. The strong force is described by a theory called QCD, or quantum chromodynamics. So there's a very peculiar feature of the strong force, or QCD, which is that if you look at the potential between a quark and anti-quark, what you see is that at short distance, it's dominated by this Coulomb-like potential that you are all very familiar with. However, as you go to a larger and larger distance, and these linear potentials start taking over, which means that as you try to separate two quarks, you are going to get this potential barrier which increases with the distance. Or the force between two quarks keeps constant as you try to put them away from each other. This means that you will never be able to really separate two quarks from each other. And this is not the case in quantum electrodynamics. For the Coulomb potential, at long distance, it eventually goes away, and there's no problem to separate the positive and negative charge. So because of this feature of the strong force, we get the phenomena called confinement, and therefore we have never seen free quarks in nature. So QCD is a very well established theory for the strong force, as commented by by Frank Wilczek a couple of years ago, and this is the guy who invented QCD and got the Nobel Prize for it. So the study of the strong interactions is now a mature subject. So we have a theory of the fundamentals, which is QCD, that is correct and complete. So he has the very right to say so, because the QCD has stood up to the experimental test over many decades, both in the very long distance regime, in the calculation of the mass of the various hadron states, to the short distance regime in predicting how the coupling constant runs with the energy scale that exchange in the interactions of quarks and gluons. And what is very interesting is that it was found that the coupling constant actually becomes smaller and smaller as you go to shorter and shorter distance or higher and higher energy scale. The interactions among quarks and gluons gets weaker and weaker as they get closer. And we give it a name of this phenomenon called asymptotic freedom. So if QCD is so well understood, so what's still left to be studied? So the condensed matter physicist Phil Anderson made this famous remark that more is different. So with 1 water molecule, you don't feel wet. However, if you put billions of billions of billions of water molecules together, we get something like this. And then if you cool the temperature down, and then we get that. So the point is that even the QED has been understood so well to incredible precision at the fundamental level, it is still not possible to predict the behavior of the complex many-body systems. For example, different phases of the water. And we call this the emergent phenomena of the many-body system, which may follow their own basic laws, and those may be just as fundamental as the fundamental interaction Lagrangians. So therefore, our goal, the goal of our field is exactly to try to look for possible interesting emergent phenomena of many-body QCD system or strong interaction system, because QCD is much more complicated theory than QED. So there's good reason to believe that there could be interesting new emergent phenomena of the QCD method, right? So we do have some theoretical guidance from lattice QCD calculation in terms of whether there could be emergent phenomena of the QCD method. And the QCD potential that I showed you earlier, this linear potential, is actually for a system that at relatively low temperature. And as if you can manage to increase the temperature of the system, and it's predicted that at a certain point, at sufficiently high temperature, this potential is going to be modified in a way that it's going to become a constant as a function of the distance. So at that point, and you can imagine that there will be no problem for two quarks to move away freely from each other. So this potential barrier is gone, and we may reach a phase of what we call deconfinement. So the quark and gluon, they are not bound together inside the hadrons anymore. So more quantitatively, so this is calculation of the QCD equation of state, which shows you the ratio of the energy density over temperature to the fourth power, which essentially gives you the degree of freedom of your system. And at very low temperature, we are supposed to be in the confined hadron phase. And as you increase temperature, and at some point, your degree of freedom of system rapidly increase, and then reaching a plateau. This is a sign that the quarks and gluons get released from the nucleons, and it reaches a plateau that is very close to what's called the ideal gas limit for completely non-interacting quarks and gluons. And the predicted transition temperature is around 2 times 10 to the 12th Kelvin, or 2 trillion Kelvin, or 154 mega electron volt in the unit that commonly used in high energy physics. So because of that, we believe that at very high temperature, we will have a system of liberated quarks and gluons, and they are weakly coupled, weakly interacting, behave like a gas system, and we call it Quark-Gluon plasma. So this is the conjectured phase diagram for the QCD method. On the vertical axis is the temperature. The horizontal axis is called net baryon density, but you can just take it as the pressure of the system. And this orange region is believed to be in the phase of the Quark-Gluon plasma. And in particular, at Large Hadron Collider, we're interested in at around 0 net baryon density or pressure, if we can go up in temperature, and at some point we should be able to cross this, we should be able to transition into a phase of Quark-Gluon plasma, and we would like to explore possible novel properties of these states. And this is what I'm going to focus on in this region, the very high temperature and low pressure region. Although there has been active research going on to explore other parts of the phase diagram. So the QGP actually have existed in the evolution of the universe in a very early time, about up to a few microseconds after the Big Bang. You can imagine the energy density is extremely high, the temperature extremely high. There's no chance for the nucleons to exist, and we should be in a phase of the Quark-Gluon plasma. Now, in order to study this primordial Quark-Gluon plasma, of course, it's not possible to go back in time of the universe, and the only way to do that is to try to recreate a little band in the laboratory. So how can we do that? This was first suggested by T.D. Lee in this, his seminal paper in 1975. So he said, first, in high energy physics, we have concentrated on experiments in which we distribute a higher and higher amount of energy into a regime with smaller and smaller dimensions. So this refers to the traditional high energy physics like E plus, E minus, proton-proton, electron-proton collisions, and colliding these small objects, and we'll try to probe smaller and smaller scale. However, this is not what we want. In order to study the question of vacuum, we must turn into a different direction, and we should investigate some bulk phenomena by distributing high energy over a relatively large volume. So we need to create something that's relatively large so that we can actually call it a matter, right? So study is a global phenomenon, and possibly a collective and emergent phenomena. And the way to go is, instead of colliding small objects like proton, we can collect large nuclei, like gold or lead nuclei. We accelerate them to very high energy and smash them into each other, and hopefully that will make a difference so we can produce something new. And for those objects, the transfer size of a nucleus is like 10 on the order of 10 Fermi, so it's significantly bigger than protons. So there are two accelerators in the world that collide heavy ions. So first is the relativistic heavy ion collider at Brookhaven National Lab in New York. And the first collision happened in in the year 2000. And they mainly collide gold ions up to an energy of 200 giga electron volts. But meanwhile, they also collide a variety of different types of ions. And 10 years later, in 2010, the Large Hadron Collider was turned on, and the main purpose of the LHC is to collide proton-proton, but it also spends about 4 weeks every year to collide lead nuclei or proton lead nucleus at about 25 times higher energy. I'm not, so I guess you are probably familiar with the LHC when the Higgs was discovered, so I will not go into a lot of details. So I'll just show you a nice picture of this detector I'm working on, and also the Kansas group is working on the CMS detector. Here you can see there's a person here. You can get a sense how big the experiment is, and you can see how complex this experiment is. It's quite amazing that such a project actually works. So this schematic shows in more details what CMS detector looks like. Again, I will not go into great details. It's a general purpose detector and try to capture all the particles that produced by a collision that's happening around in the center. And basically, it's basically like a high-resolution camera that we're trying to take pictures of the collision that's happening at a very high rate. So I want to show you a cartoon of how the heavy-ion collision evolved. So initially, we start with these two pancake-like ions because they are highly Lorentz contracted, and they'll come in and they will hit each other. And right after the collision, the Quark-Gluon plasma is produced. It is the red stuff. And they will quickly expand and cool down, and in the end decays into the final state baryons or mesons. The whole fireball lives for about 15 Fermi over the speed of light, or 5 × 10⁻23 seconds, and with the transfer size on the order of 10 Fermi. And so this is what we see in the end in the experiment. And this is the event display recorded by CMS for head-on lead-lead collisions. And here, so each this curve represents the particles coming out. And in this collision, there could be up to 20,000 particles produced. It's quite amazing. And so if we assume that there's a matter formed, based on how many particles are produced, we can try to estimate what is the energy density that of the medium, and you get something like 10 to the 19th kilogram per cubic meter, and this will be like 20 times of the normal nuclear matter. It's really it's very dense, and it's highly likely that we are in a new phase of the Quark-Gluon plasma. Now, to give you a sense what the event look like in a proton-proton collision, in a small colliding a small object, and this will PP collision at a similar energy, and overall you get maybe 10 or 20 particles per event, which is way different from what we get here. So do we actually really created a thermalized and hot medium? We do have more evidence. So for example, this is a measurement from the Alice experiment, and Alice is a dedicated heavy-ion experiment. And they measured the transverse momentum distribution of the photon coming out of lead-lead collisions. And if you compare to what you expect from the proton-proton collision, which is indicated by this blue line, you find that at a very low momentum region, there's an excess of the photon, which more or less follow exponential shape spectrum. And we believe these are the photons, these are the thermal photons radiated from a hot Quark-Gluon plasma. And from the slope of the exponential, we can extract the effective temperature of the QGP, and that's about 300 MeV, and so we conclude that the initial temperature of the QGP must be much larger than 300 MeV, and which is way beyond what's needed to cross the phase boundary and reach the QGP phase. So if the discovery of QGP is expected or is exactly our goal, and what is the total big surprise is how the QGP actually behaves. So remember that I told you that so we expect the QGP to be a weakly interacting gas of quarks and gluons. However, in 2005, the RHIC experiments released the press release, issued a press release summarizing the main findings in the first few years of RHIC operation. And what they concluded is that if you look at the last sentence, they found that the QGP created appears to be more like a liquid. So this is completely opposite to what people have expected originally. And actually, there's more than that. Not only QGP is a liquid, and we found that it behaves like almost nearly perfect liquid or perfect fluid with almost no frictional dissipation or with almost no viscosity that flows better than basically any known type of matter. So I'm going to explain to you what all this means in a moment. So you imagine that you start with a bar of gold, and you heat it up to 100 billion degrees, and it goes from a solid to a liquid, and then in the end vaporize, become a gas. And then after that, you make it 20 times hotter, and then it turns back into a liquid again. It turns back into a soup of quarks and gluons. And so our early universe is more like a soup, a hot soup of quarks and gluons. So this, I find this is really amazing, really surprising. So how can this be possibly realized from the first principle QCD? And we don't know the answer. And could there be other phases, at higher temperature or density in the phase diagram of the QCD matter? So these are the questions that we are interested in to find the answer to. So let me explain to you how we find out it's a fluid. To do that, I want to discuss a different system, which is called atoms at very low temperature, lithium 10 to the minus 7 Kelvin. And this system is initially trapped in to have this cigar shape, and then they suddenly remove the magnetic trap and let it evolve. Then you take pictures at subsequent times, and what they find is that the system expands, but the expansion rate is not symmetric. It is much stronger along the short axis of this cigar shape. And in the end, when you look at the final state, you find that there are more atoms coming out along the x-axis than the y-axis. You have some asymmetry in the azimuthal direction in the final state, and which indicates that the system is strongly coupled, behave like a fluid, where there's a pressure developed that that is stronger along the short axis of the system because it's more squeezed. And imagine if the system is like a gas where the particle will not interact, they will just fly out, and you get, in the end, you are going to see pretty much a spherical cloud. So I use this analogy because the idea is exactly the same in heavy-ion collisions. In the off-center heavy-ion collision, the overlap region looks like this elliptic shape, and which means that in the transverse plane, you have this symmetry in phi direction, and this, so undergoing this fluid-like pressure-driven expansion, and in the end, in the final state, we see azimuthal anisotropy in the particle's momentum space. So this is the data, and you can see they can describe very well by a cosine 2 phi function with the coefficients called V2 and we call it elliptic flow. And this is quantity we are interested in. We are interested in quantifying. So if doing a Fourier decomposition is too complicated for you, and we can even look at the event display event by event, and you can clearly see that the ellipticity of the event is a very striking effect. So that was a 2D, two-dimensional transverse view of the elliptic flow. Now I want to tell you how the elliptic flow looks like in 3 dimensions, because the particles are produced over 3-dimensional phase space. So if this is where the beams comes in and collide, so we'll produce the particles produced with a specific azimuth of phi, and also the theta polar angle direction. So this defines a momentum vector of the particles. And so in high energy physics, instead of using the polar angle, we define another quantity called pseudo rapidity, which is for good reason, and but it's basically a measure of the polar angle in the angle in the longitudinal direction. And then we can take another particle that's going in different direction, and we are interested in how these particles are correlated with each other in this eta rapidity and phi space. So we want to look at the distribution of all the particle pairs that we can build out of all the particles produced, and how they are distributed in the relative difference in their pseudo rapidity and azimuth angle. So if we perform that measurement, and this is what we get, and this is for the off-center lead-lead collision, and the particle pair density as a function of delta eta and delta phi. And there are 2 distinct features that you can see from this distribution. The one is that there's this little spike here around delta eta and delta phi equals to 0. So I'm going to cover this up for the time being. I want you to focus on the rest of the structure, which is almost completely flat, but along the delta phi direction, you can clearly see this cosine 2 delta phi shape, and this exactly comes from the elliptic flow. The elliptic flow is almost nearly invariant at different rapidity slides. If you look along the longitudinal direction for particles produced at any rapidity slice, you see almost the same ellipticity. And this makes sense because this elliptic flow is developed from the initial elliptic shape of the overlap region, which looks the same at any position along the beam axis. And to convince you that we do have something new here, and this is how it compares to proton-proton collisions, where what you see is quite different. And the structure we see in proton-proton is well understood. It comes from a process like this, where you scatter 2 quarks, and the one of the quark will break up into many particles that will give you this spike that all the particles are quite collimated with each other. So the most important part is that we don't see anything in this region compared to lead-lead, and around delta phi equals to 0 and large rapidity gap. You see there's not compared to lead-lead. The lead-lead has this long-range structure, which we call near-side ridge, which is a clear signal of the collective effect. Okay, so let me show you data. This is the elliptic flow data plotted as a function of the transverse momentum of the particle, and for measured from CMS. And so V2 increases with the momentum of the particle. And so different panels represent the different impact parameter class that from left, you are looking at collisions that more head-on. As you go toward right, and the collision becomes more off-center. And you can see the V2 go from the central to the peripheral events increase, which makes sense because your V2 is the response to the initial lenticular geometry, and as your system gets more asymmetric, then it goes up. We can also compare to the RHIC measurement at much lower energy, 10 times lower, and we find the V2 is almost on top of each other. This is interesting. It means the QGP fluid at 2 different energy seems to behave similarly. We can compare this to a theoretical calculation, which is basically the hydrodynamics from fluid dynamics, but we run a relativistic version, and we take some initial state, and we find that the data are very well described by hydrodynamics with almost one impact parameter, which is called eta or S. So eta here is not pseudo-rapidity, actually it's called the shear viscosity over the entropy density, and this ratio, we need a ratio of 0.2, and which is a very small value. So 0 will mean that it's perfectly ideal hydrodynamics. Let me quickly explain to you how the shear viscosity would affect the elliptic flow. So assuming you have different layers of fluid, they have a symmetry, they move with different velocity. The shear viscosity will dissipate the momentum from the layer with high velocity to low velocity. So in the end, what you get is that the asymmetry gets reduced. So the shear viscosity is the effect of the momentum, gives the effect of momentum dissipation, which will lead to less elliptic flow. And so according to the kinetic theory, the eta or S is a measure of the mean free path of the system. And in the limit of the ideal gas, the mean free path will go to infinity, and same for the eta or S. And for the perfect fluid, your interaction mean free path is 0, and the eta or S is also 0. So 0.2 is very close to 0, so it's very small. And for materials like water, it has smaller eta or S, and for stuff like honey, it flows less well, and it has larger eta or S. So this is a combination of the shear viscosity as a function of temperature around their critical temperature for different type of fluid. To give you an idea, and for water, the eta or S is around 2, and for helium, liquid helium is on the order of 1, and for the Quark-Gluon plasma we produce, it has an eta or S that is down here, around on the order of 0.1, 0.2. This is very small. It's so small that it touches this dashed line here, which is a lower bound, the minimum viscosity possible, conjectured from the string theory from ADS-CFT correspondence. And these guys, they conjecture that for any type of strongly interacting fluid, the eta or S cannot be smaller than 1 over 4 pi, which is like 0.08. So it's interesting that the string theory finds some applications in reality, so in the heavy-ion collisions. Well, at the moment.
Now that you mentioned that,
yes.
you'll object and say that's a hoax.
Yeah.
You know it's a hoax.
Yeah.
And everybody knows it's a hoax. So I don't think it should be promoted. But you could try to defend it if you want.
I'll not do it at this point, but yeah, it's true that.
It's not string theory. This is a dimensional analysis. Result, and its application to physics is a hoax, and it's not nice to lie to people. By them, you're not lying, but they lie.
Okay. I'll take it as a comment. So.
You knew that was going to happen, right?
So as you can see, so right now we still have quite a large uncertainty in terms of what's the exact value of the ether S of QGP. So in particular, so whether the ether S for QGP is actually really close to this conjectured bound, or maybe smaller. And so currently the main experimental uncertainties come from how we model the initial condition of the collision. We know it has this elliptic shape, but what's the eccentricity of the ellipse? And that we have some idea, but we don't know exactly what that is. To improve that, actually, we know that the initial shape of the QGP is not perfect ellipse. There are noise, there are quantum fluctuations. If you look at it event by event, it's actually going to look like something like this. And you have these random hotspots. And to the first order, it looks like ellipse. But actually, I believe you can actually draw a triangle around it. And this triangle geometry, again, under the pressure-driven expansion, is going to give you a triangular anisotropy, which will give you cosine 3 delta phi correlations. And you can keep going on. And all these higher order monopoles of the initial QGP shape will produce the anisotropy that you can observe in the final state. And this is in analogy to the CMB power spectrum. Of course, and we only have one event of the whole universe, and we can decompose them into different monopoles and look at the power distribution of different monopoles. So I think I'm a little behind, so I'm going to skip some of the slides. And I just want to show you. So this higher order anisotropy has been very well measured experimentally. I showed you the data for V2, the elliptic flow. And we also measured V3, V4, and V5 for different collision geometry as a function of momentum. And these curves are the same hydrodynamic calculation. And you can see they all agree very well. So looks like the hydrodynamics faithfully transpose the initial noise into final state momentum distributions. And this noise is actually our signal. It can help us to constrain much better the modeling of our initial state of the heavy-ion collision, and therefore can constrain the extraction of the ether S value. So we can also study elliptic flow for different type of hadrons, and this is the measurement from Alice. And what you see is that for different type of particles, they follow different curves, and these curves, they are ordered in a specific pattern by the mass of the particle, which is exactly predicted by the hydrodynamics. Okay, so up until now, so everything looks very, very nice. So the whole paradigm of the perfect fluid Quark-Gluon plasma seems to be produced in the heavy-ion collisions. However, things has yes.
What's happened in regards to G?
So.
The blue curve doesn't go through the blue box.
Yeah, right. So at large momentum, we expect the physics is going to change. So the hydrodynamics, you really describe the physics at low momentum around the temperature of the Quark-Gluon plasma. And as you go to high PT, then you expect the hard scattering of the quarks and gluons to take over, and therefore you don't actually expect they describe the data. So they do not agree, but it's not something we have to worry.
Well, if this is a hydro prediction, what happened with the P bars? Is that the red dots?
So P bar, no, the proton is the red.
Why are protons different?
Yeah, so the quantitatively they don't exactly match. But I think the point here I want to show that the ordering by the mass is at least qualitatively consistent with hydrodynamics. At the quantitative level, there are still subtleties. However, in 2010, we had breaking news. So remember that I said that we don't expect to create a QGP in small systems. They are too small. Therefore, we have to collide large nuclei. However, in 2010, after we just recorded first data of the proton-proton collisions, and we did analysis of the two-particle correlations and look at the pair distribution in delta eta and delta phi in proton-proton collisions. And now you see that we can see this what we call near-side ridge. This elongated structure is tiny there, but you can actually clearly see that around delta phi equals 0. And as I told you, and that will be a signature of the collective float, as you've seen in the heavy-ion collisions. But why we don't see that previously, when I show you proton-proton collision, because here we actually require a special type of proton-proton events where in a single collision, a large number of particles gets produced. For this case, at least 110 charged particles gets produced. And these are what we call the high multiplicity events. So in a single proton-proton collision, you get massive amount of particles produced. It's almost like a heavy-ion collision. It doesn't look like a normal PP collision. And the typical PP collision will give you maybe on the order of 15 particles. And here we're looking at a couple of hundred particles produced from PP collision. And these events are rare. They occur maybe 1 in 10 to the minus 5 or 10 to the minus 6 probability. And so we want to ask, so maybe we have created a much smaller Quark-Gluon plasma liquid with much smaller size of on the order of Fermi. So I think it's fair to say that no one has expected that, and this is beginning of a secondary discovery phase. Discovery not in the sense of discovering new particle interaction, but discovering a new phenomena that we have not anticipated. So if the effect in PP collision is so tiny to be convincing, and the real game changer is the proton-nucleus collisions at the LHC in 2012, where you collide the proton with the nucleus, and you can see the intercept of the proton nucleus is also very small. Right? It's still about the size of a proton. And there, so immediately, the 4 experiments have performed the measurement of the two-particle correlations, and all of them has reported the observation of this long-range correlation structure. And in P-like collisions, you can even clearly see this cosine 2 phi shape along the delta phi axis. And the effect is so strong that one can actually do the real flow analysis, try to decompose with the Fourier series and extract V2, V3, and so on. So at this point, I think people take it more seriously that there may be collective effect and QGP fluid in these small systems. So after that, so this made people really rethink. So what's the real criteria for making a Quark-Gluon plasma? What's the criteria to create a QGP fluid, and how small can it be? When speaking about the applicability of the hydrodynamics, actually what matters is not really the absolute size of the system, but how the size of the system compared to the interaction mean-free path, right? Heavy-ion collisions, the size of the system is under 10 Fermi. We conclude that the interaction mean-free path must be a lot smaller than 10 Fermi. But how small that is, we have no idea. And what we know is that if we look at the normal PP collisions and we shrink the size to the order of Fermi, in the normal PP collision, we do not see any sign of collectivity or collective flow. However, we asked the question, so what if we can make it much denser by increased multiplicity and look at these high multiplicity PP events with the same system size, but by increasing the density, so maybe we can significantly reduce the mean-free path and make it much smaller than the size of the proton. So where's the limit? Where's the limit in terms of how small the QGP can be? Where's the limit in how small the mean free path can be for a QCD system? So we don't know the answer. And let me, I think I'm going to skip a couple of slides, and I want to show you some data. So let me show you some more evidence that, so indeed in these small colliding systems, we see clear evidence that a QGP fluidized material has been created. And here we are looking at the elliptic flow data for measured by CMS for different type of particles, 3 different type of particles in 3 type of collision systems. So one is the heavy ion collision, the proton-ion collision, and proton-proton collision. What we found is, what I did here is that actually I removed the legend from this plot, but what I can tell you is the 3 panels corresponds to 3 different systems, and what you find is that there's almost no way that you can tell which is which. If you put them side by side, they almost have the same behavior. You can see, if you look at low momentum region, you see what's called the mass ordering that I showed you earlier, which is consistent with what we expect from hydrodynamics. It happens for all 3 panels. And so here on left is PP, middle is PLED, and right is LED. And what's very interesting is that in the small system, the splitting you observe is actually even larger than this large system. And the reason is that for smaller system, you have the same total energy, same total multiplicity, but small system, the density is higher. Therefore, the pressure is stronger, so it pushes out stronger and generating a stronger effect of the mass ordering. Now, I have been using the word collective effect, collective flow, but so most of the results I showed you before is only derived by correlating 2 particles. We have not actually shown that so all the particles in the event have participated in the correlation we observed. But that can be directly addressed by measuring the elliptic flow by correlating more particles at the same time. It's like doing the cumulant to higher and higher order to see whether the elliptic flow you extract depends on how many particles you look at the same time. So here again for 3 systems, we compare side by side. This is the V2 extracted by 2 particle correlations as a function of the total multiplicity produced in the event. And again, you see the behavior in all 3 systems are quite similar, right? So at certain multiplicity, the flow effect starts to turn on, and it makes really no difference whether you look at PP or look at LED. And then what we do is we can, instead of correlate only 2 particles, we can correlate 4 particles at the same time. Then we get the blue. It's a little below what you get from 2 particle correlation. Then we can correlate 6 particles, and we correlate 8. And we can even correlate all the particles using a technique called Liang zero. And what you find is that these multiple particle correlations give you the same V2 value. So it doesn't matter how many particles you correlate to measure V2, you always get the same value. So this is a direct evidence of collectivity. So this shows that this correlation is truly collective, involves all the particles produced in the event. And you can get it in any hadronic system. It doesn't have to be heavy ion. Even in proton-proton collisions, everything seems to float. So you can ask question, do we really have to collide heavy ions, looks like all the physics is already there in proton-proton. So I want to wrap up. I quickly discussed a little bit about the future. So we have observed the flow of the quark-gluon plasma. However, the question that we don't know the answer to is that, so why does it actually float? How do we understand it from the QCD? What is actually flowing? Is it quarks and gluons are flowing, or there are other quasi-particle degree of freedom in the system? So how small is this mean-free path of the QGP? And this is quite a relevant question, because in the kinetic theory, you can relate the interaction mean-free path with the temperature of the system and the coupling strength of the system. The G is the coupling. Now, if you think the G is the order of 1, so this is a very strongly coupled system, then you would require that the hydrodynamics applies when the size of system to be much larger than 1 over the temperature. However, unfortunately, I have to mention string theory again. This is a recent work that using ADS-CFT correspondence. In their scenario, they have the infinitely strong coupling. So the G goes to very large value. So in that case, you can see that you don't need to be L to be very large. You can also fulfill the hydrodynamic criteria. And therefore, you can have a fluid-like system in a system that's as small as a proton-proton collision. So I will not comment on this, but just want to show you that what we are trying to study really have quite important implication to the fundamental properties of the system. And for the future, to get more insights, and what we can do is we can vary our system size. We can collide larger object and small object. And at RHIC, actually, they have a very flexible program. You can collide deuteron with gold. You can create helium-3 with gold. You can collide proton with aluminum. So any kind of all those things. By doing that, hopefully we can map out more details about details of the property of the fluid we have created. And a second approach is to try to make use of the penetrating probes. And this is actually a big area in our field that I didn't have time to mention. But the idea is that there will be hard probes that are generated inside the QGP, like the digit, energetic quarks or gluons. As they go through the quark-gluon medium, they will lose energy, and they could get lost. A phenomenon we call jet quenching, and this is a striking effect that we can clearly see in the heavy ion collisions. And this is the event display from Atlas experiment, where you see on one side you have a high energetic spray of particle coming out, but on the other side you don't see anything. The mostly is very soft particles. In this way, we can really see whether we can see the scattering point inside QGP. For example, for the QED fluid, we know that the water cannot be smaller than a water molecule, right? So that gives us some lower bound, the size of the water molecule. So is there such a fundamental scale in the QCD fluid? So this is something hopefully we can get some insight from the program of hard probes to try to really probe the constituent that is flowing inside QGP. So I think this is just so quickly what's going to happen in the future. So currently, the program of the ions has been planned until 2030. We'll be colliding this year the proton-nucleus collisions, and then in the next 10 or 15 years, the goal is to try to increase the statistics by a factor of 20, hopefully, and try to, hopefully we can solve the mystery and even better to make a new discovery. And here I will quickly summarize. So we have clear evidence that a strongly coupled hot quark-gluon plasma is created in heavy ion collisions, which behaves as a nearly perfect fluid with a very small shear viscosity. And I show you with analogies, there's intriguing connections among seemingly disconnected field like the QGP, the cold atoms, and the string theory. So all these fields are trying to address the system that is strongly coupled, strongly interacting, many-body system. And we have observed unexpected evidence of the QGP fluid in small but high multiplicity systems like PP and PLED collisions. And there are still a lot of questions that are open to be addressed. For example, are we really seeing a tiny QGP droplet there? And how small can the QGP be in size? And I didn't have time to mention this point, but so in the end, let me say that we have an exciting program that planned to probe the QGP fluid using hot probes and varying the system size in the next 15 years at LHC, and hopefully we will finally address the question like why it flows. So with that, I'll end here. So thank you for your attention.
So we have time for a couple of questions for Wei.
Okay, so you've convinced me we don't need any lead running anymore in the LHC. So why do we need you guys when you run your PP collisions? Why can't you use the high energy ones? Is it because your trigger has to look longer or what? So why can't you use any of the PP data that we're taking to actually study all of these effects?
Okay, yeah, that's a very good question. So the reason is that the normal PP collisions has very high pileup. So in one event, there could be 20, 30 collisions. And the signature, the events we are interested in is high multiplicity coming from a single collision. So if you have pileup, then when you see a very high multiplicity, you don't know whether they come from just many, many more normal PP interaction, or it's just come from single event. If you have, of course, if you have a perfect vertex resolution, you'll be able to identify every single collision very well. Then that's possible, but at some point the interaction got too close. You simply don't know whether the high multiplicity events is a single collision or multiple collisions. So that's the main. The main issue is the pileup. The data I showed, they are recorded with special conditions. Either we have to request the machine to displace the beam to create very low pileup beams, or during like the Vandermeer scan, the pileup is low, we can record some data. So that's the main limitation.
Yes. Do you think that this quark droplet thing might exist in E plus minus collisions? So like E plus minus collisions, you can produce quark anti-quark here. Yeah. And so you can have really high multiplicity events like that. There's no initial state hadrons involved.
Yeah. So if you asked me this question a few years ago, then I would say no. But after what I've seen at the LHC, I think I would say this is possible. Because it's possible that what's interacting is just the field. It doesn't matter what the initial object is. Then you have the field colliding and strongly interact and develop into some fluid-like state. And so in this sense, I don't see why it's not possible if you collide electron ions with electron proton, even proton, it's possible. Actually, many people believe that at least in electron ion, electron proton collisions, we should see a near side ridge, like collective flow. So I would say Yes. Yeah. And if we have the data, we can go back to look at those data. It would be very interesting to see whether it's there. Maybe it's already there, we overlooked.
What was the eta over S value of your honey?
That is a few thousand. It's a few thousand, yeah. Yeah. So it's pretty good fluid. The QGP is pretty good fluid.
What is 8 over S for free field theory?
For free field, you mean the
Well, interacting field.
interacting
You have a notion of entropy.
Yes.
And it's, so there's no dissipation.
Yeah. So you would.
8 over S is 0, is that right?
No, you will diverge. Well, I mean, for completely non-interacting, it's hard to imagine, but you can gradually approach to the limit of weaker and weaker interaction. Then the iterations will diverge.
It's big.
You get big. You approach the ideal gas limit, the mean free path will get large, and iterations get large. You will never. A small perturbation will.
How does that work? Because eta is about viscosity and eta is about dissipation, and entropy is just statistics. Why doesn't it go to 0? We have a very weakly interacting system with very low dissipation.
Yeah, I see. To be honest, I don't know the answer. I don't know the answer.
Let me maybe change around a little bit different. At the end, you mentioned G goes to infinity, a very, very strongly interacting system in order to have a reason why you see these collective things even in PP. So, does that sort of scenario lead to the perfect fluid with low viscosity? Low 8 over S? Is it suddenly a separate topic? Are we still talking about low 8 over S in that scenario?
No, eta S is a dimensionless. Is the dimensionless.
It is in this now that you went to infinity.
That will be a separate issue.
This is
yeah,
completely different.
This will depends on the eta S is also depends on temperature,
Yeah.
and we don't know. So it could be that at infinite at very high temperature it can become very big, and so then that means that even this condition is not enough. So eta S. So the whole discussion here is an assumption that eta S is small. But in ADS-FT, so eta S also depends on the coupling. Also depends on temperature, and they can be small, can be big.
So maybe with that we should thank the speaker again.